Well, welcome everybody from my side as well to this workshop showing the high record achievements. We have seen how we started by building models for molecules and identifying good solvents for the CO2 capture. Now we also have the technology that accommodates the solvent to have a economically viable carbon capture process. We have reduced the rotating pipe bed technology has reduced the capital expenditure by a large percentage, and we have seen also the ability to also integrate the reboiler with the regenerator, so even further intensifying the regeneration of the solvent. That means not just like a reduction of the capex, but also reduction on the energy that is required for the regeneration. High record is building the unit for a 10 tons per day of CO2 captured. I think demonstration will start in about 6 to 7 months from now in 3 different sites. One is going to be, as Saki said, a line production site, a gas-fired power plant, and a refinery. So like big variety of flue gas streams with different content of CO2, different operating, let's say, regimes. The power plant has like a very variable operation. The line also manufacturer is operating on a cyclic mode, and the refinery is using large variety of fuels, whatever is available at the refinery. Okay, so we have now we're open for questions to John and James from the audience, and so please free to yes.
In which loading concentrations do you the concentration of the CO2 per molar element in comparison to the traditional process?
Yeah, it varies depending on the CO2 concentration of flue gas. I think if you're working with a more dilute flue gas with, let's say, from a natural gas combined cycle turbine, around about 3 to 4% CO2, then you would need to have a lean unloading within your solvent in order to get the driving force of the absorption. Because if you're trying to achieve 90% capture, you're going from, say, 4%, you need to get down to 0.4% in your outlet flue gas. So the driving force there comes from the lean loading solvent. Whereas if you're operating in a cement plant or equipment plant, you've got 12% CO2, you don't need quite as much driving force. So it varies depending on the industrial application. But yeah, we would typically, the sort of loading ranges are similar to MEA in comparison, because ultimately what you're looking to do is get the right delta in order to be able to achieve your percentage capture, your degree of gas separation.
I mean, today's CO2 absorption plants, is that you come nearby the equilibrium point. Yeah. So, and as I give a number, so we play between the rich and the mean solution between the 0.5 and 0.25. Yeah. So when you do not have this loading, then you need more liquid, which you have to circulate. Yeah.
Yeah. So I think the point we're making is like, with our solvent, we have a higher equilibrium rich loading than NEA. So in terms of overall cyclic loading, we have the potential for 1.5 moles per litre more in CDR max than you do with NEA. But the reality of an operating plant is you don't actually go as close to equilibrium as you see in the experiment. We're always operating further away from the equilibrium that we would like to be. So it doesn't always matter that much.
When you get the high concentration, yeah, your liquid flow rate goes down, and the capacity which you have to heat up. Yeah? This is your defining your CapEx.
Yes, it can. So when I think I didn't present any of the test data, but a lot of the work that we've done with the rotating pack beds, the Artemis project once on the demonstration, we've done direct comparisons with NEA. Our liquid to gas ratio is lower than NEA. We can achieve higher loadings in our solvent, so we do operate at a lower liquid to gas ratio, which means exactly what you're saying. We have lower liquid flows through the generator, and we have less energy being required to regenerate the solvent to get that specific capture rate. So I think if the question is, do we see advantages of the solvent based on lead-rich loadings? Yes, we do. I can't go into the specifics about exact values because that varies depending on what the application is. But we see this. We've got lots of test data that we've been able to make direct comparisons with NEA in this case. So that's where our energy reductions come from. It comes from the reduction in the flow rate, less water being put through the stripper as well. So actually, we compare to 38% MEA. That's a lot of water. 70% water when you're working with MEA. That's a lot of latent heat that you have to put in the steam in order to recover the CO2. In our solvent, we have less water, so there's less latent heat required in order to vaporize it. We have the lower flow rate, so it's a combination of those factors. That's where we get energy reductions.
If I would like to somehow facilitate the discussion and also like expand a little bit the scope of the discussion. As I mentioned before, the flue gas stream may have variation in its flow rate and also in its CO2 concentration. So the question goes to you guys, like, do you believe that the RPB or the CDR max are capable actually to provide a flexible operation to accommodate a large range of variability?
It was a gas-fired boiler, but we also installed a cryogenic CO2 tank. So we would produce the boiler was naturally, well, the way it was normally operating, we produce a flue gas with a concentration of about 8% CO2. Depending on what the excess air was, we could also use a blower to dilute that flue gas so that we could have a lower CO2 concentration, so we could simulate different industrial applications, as well as introducing cryogenic CO2 to simulate higher cases, so up to 20%. So we tested extensively with the RPBs, with our solvent MEA, a wide range of simulated flue gases that represent different industries. We've worked, I think, extensively shown that the RPBs have that flexibility to capture 90% or more of the CO2 across a range of CO2 concentrations. That's actually our experience with our solvent. What I was kind of alluding to with the C1 series is that we will be designing these for specific applications. So C1 series that will be able to capture 100 tons per day, or low CO2 concentration flue gases. There will be a series that will then be able to focus more on the mid-range and the higher CO2 concentrations. So we realised that the demand for the technology comes from a large cross-sector of the industry, different applications, and we're accommodating that so that we can provide the technology that scales are required for the amount of decarbonisation that each site has. So yeah, the rotating packed bed, CCC, has that flexibility and can be a solution. I think up until a certain scale, I think I showed around 850 tons per day. We think that's at the moment that's roughly the limit that we can achieve in a single train. And then actually just when we get to that sort of capacity, we start thinking, is this the right fit? So we see that the modular technology is a good fit for mid-scale industry, maybe not mega power plants that are mega scale.
John, are there any other secrets that need to be revealed for the operation of the RPB? You mentioned, okay, it's an old technology, but it's only very recent that we're actually doing such a thorough investigation, and especially for the CO2 capture. I like those diagrams with the distribution of the liquid phase, but are there any other secrets that we need to reveal so we can make it even more efficient?
CO2 with the flow rate can change over time. So we always say rotating packed beds can be used for those transient systems, and they do have response times of seconds. So even those two big absorbers that we see for high record will respond within less than a minute to a change in the flue gas. So the fast response is good. What to do about it? You don't have that many options. RPBs have a very flat response in terms of rotational speed versus performance. So when you get away from the rivulet flow regime I was talking about, there's not much change in mass transfer performance. When you're into spray and film flow, it's quite flat. It does increase slightly as the speed goes up, but not much. So probably with a rotating packed bed, what you'll have to do if you get an increase in the flue gas concentration and flow, is push the liquid flow up a little bit to accommodate that.
Other questions from the audience, please? You may want to say your name and your affiliation.
You correctly said that your study was the reduction of CapEx and OpEx. It's another important aspect in the industrial plant, which is the RRP. Now, we are replacing the absorber system, which is a static equipment, on the oil heavy equipment, the integration pump, with the whole rotating equipment in the upstairs, which is the expected system. You have a sort of feedback of continuous time operation of force, and which is the expected impact on the reliability related to this calendar.
I think it relates to what John was just saying, actually, that the response time of rotating packed beds is quick. In the example, again, the example that John's given, the host sites where we're going to be operating a high record are not going to be operating 24/7. They're not going to be running in continuous steady state. We've got the quick line plant, which basically operates it as two gear ones, switches between them. So we have periods where we have quite a lot of fluctuation in CO2 concentration. We also have periods where it's not going to be producing flue gas as well. So we've got these challenging operating conditions. And yeah, we feel that the rotating packed beds are very suited to this. And then with the combined cycle power plant that we're testing out as well, we know that this is a plant that is providing energy to the grid based on demand. So it's not a base loading plant. It's not operating 24/7. We're going to experience many warm and and cold startup and shutdown. But what we're seeing, and also from our demonstration in the East, is that RPBs respond rapidly. We can start up quickly. We can reach a steady state quickly as well. So I think plant availability is, it's something that we can't control, but we can make the technology to be responsive to kind of work with that plant rate.
Pardon? It is still not available maintain to fail. You expect
What in the carbon capture plant? I mean, it is rotating equipment and it does need maintaining, and you would design maintenance cycles that are appropriate. I think in the test work that we've done so far at pilot scale, the parts that failed were the seals. But we can replace the seals, and we can also design them in a better way. I think partly the reason why they failed is because of the fabrication of the unit, and perhaps it wasn't best aligned. Maybe we didn't use the best engineering company for that particular one. But I think people build rotating equipment that's much larger and rotates at much faster speeds than rotating at beds, and they operate, they work, and they can be reliable. So I think maintaining it because it's a rotating piece of equipment is not an insurmountable challenge.
Did you ever measure like vibrations induced because due to imbalance, let's say maldistribution of the liquid phase on the disk?
The mass of liquid in a rotating bed at any given time is time compared to the mass of the rotating bed itself. So we never have detected any imbalance issues due to the liquid in the rotating packed bed. I think there was one design of RPB which is made by a company in Poland that sits on springs, and they had some issues with liquid in the case, sort of setting up a rocking. But the actual rotating packed bed itself, that liquid volume is so tiny, it doesn't affect it.
Okay.
Yeah. One last question.
Yeah, one last question, yes.
Just a question concerning the intercooler. I see that you put an intercooler between the two RPDs. So for me, because you are very efficient and you have a lot of temperature elevation, do you think that for different gas application with more CO2, or you need more intercooler, or one should be enough and you can adjust?
For amine-based solvents, one is sufficient. I think what you'll see is that in the lower CO2 concentrations, you just have less of an exotherm, and you've just got less of a cooling duty requirement in that intercooler. I don't think we need to increase the number of intercoolers. I think they can be sized sufficiently to deal with the exotherms just with a single one. I think there are some cases that there are new solvents being developed, non-aqueous solvents, for instance, and I think where the advantage of non-aqueous solvents are in lowering regeneration energy because of lower heat capacities, actually works against them in the absorption process. So rather than having water that can dissipate the heat quite nicely, they have challenges where with these organic diluents that have lower heat capacities, they have much larger exotherms, and it becomes more of a challenge. So I think when you start looking at non-conventional solvent chemistries, then you might start needing to introduce more intercoolers. But I think with aqueous amine, one intercooler is enough.
Just on intercooling, I mean, obviously you'll be familiar with this, but we did integrate heat transfer into a rotating packed bed with the absorber as well, by basically having some devices called heat pipes to remove the heat. And that had a good effect, but it is rather expensive and rather mechanically complex to have all these heat pipes in the package. So, you get intercooling in there, you can really push your performance find another factor in for an RPB, but it's probably too complicated. And one between two RPB pairs is better.